Okay, so this is going to be the lecture on equations of lines in three-dimensional space. Okay, so there's a couple of ways to describe lines in three-dimensional space. Okay, there's the parametric way and the symmetric way. So a parametric equation of a line that is parallel to a vector okay? So you have to have a vector that's parallel to, and you also have to have the point in space to describe its line. So and passing through the point, again, it's x naught, y naught, z naught. That's a parentheses, not a point of one. Okay. Okay, so we're going to have x, which equals x naught plus at, y, which is going to equal y naught plus dt, and z, which is going to equal z naught plus ct. Okay. So these are the parametric equations for a line in space. Okay. And so when we think about a line in space, okay, so we got some type of line out here just existing within three-dimensional space. Okay, then we have a point, x naught, y naught, and z naught. Now that point exists on the line, and then we have another vector that is parallel to said line, okay? And that vector is described by A, B, and C. Okay. So I'm going to talk about planes in space as well today. But whenever you're describing a line in space, what do you need? You need a point, and you need a vector that is going to be parallel to that line. Okay? Now, when I talk about a plane in space, what are you going to have? You're going to have a point that exists within that plane, and you're going to have to know the normal vector to that plane. That would be a vector that is perpendicular to that plane. So the difference between lines and lines and planes within three-dimensional space is that when you describe a line, you need a vector that's parallel. But when you describe a plane, you need a vector that's actually going to be perpendicular to that plane. Okay? So let's go ahead and start with a problem. So let's say that we just have 2 points in space, okay? And we want to describe the line that passes through those 2 points in space. Okay. Oh, I apologize. Before I get to another problem, I did say that there's 2 ways to describe a line in space. All right? So this is the parametric equation, where we have 3 equations that describe the line. But there's another way to actually describe this. Okay, so this is the parametric form. We also have a symmetric form. So, when talking about the symmetric form, so sorry, that's my email going on. If you solve for t, So this is the symmetric equation for a line. Okay. Honestly, I'll be honest with y'all. I prefer the parametric form, but writing it in its symmetric form, it can be useful at times. Okay. So how did I actually just get to this symmetric form right here? Give me a second to write that down. Let's see if I can actually fit this all on one screen. Well, anyway, I don't think I'll fit that on both screens. So what did I do? I just said, well, I'm going to subtract x naught to this side of the problem, and then I'm going to divide by a, okay? And that's me solving for t. And then for this guy, subtract y naught to the other side, divide by b, it equals t. This guy right here, subtract z naught to the other side, divide by c, and it equals t. And so that's how we get into the symmetric representation of a line in space. Okay? So just x minus x naught divided by a equals y minus y naught divided by b, and which equals z minus z naught divided by c. All you're doing is solving for t. Okay? So let's take 2 points in space and let's try to figure out what the parametric equation is and the symmetric equation is for this line in three-dimensional space. Okay. So let's say we want to find the line So, whenever you're doing this, you can get equations that look slightly different. They'll be off by a constant. Now, it depends if you want your vector to, it depends which one you pick as the terminal and the initial point. And then it matters which point you actually pick. And so you can get equations of lines that look different. But what would the major difference be between them? Okay, so in the description of the parametric equation, it says, well, yeah, x equals x naught plus at. Right? Well, that would depend on what a you picked. Okay, so the major difference between them would be you can have two different representations, but they would have different t's. They'd have different points in time. So if you said, okay, at t equals 1, I'm at this point of the line, but if I actually describe the line differently, well, t equals 1 would actually be at a different point in time. But it would still be the same line. All right? So I'm going to pick this one to be my terminal and this one to be my initial. Okay? So I need a vector A, B, and C. Okay? So it's terminal minus initial. So that would be -7 minus 12. Okay? So that's that point and that point. And then 9 minus 9. All right. And then my other one would be 11 minus -13. Okay. So that would come out to negative 19, and then 9 minus 9 would be 0, and then 11 minus negative 13 would be 24. Now, it does not matter which point you pick to actually describe the line. So you have to have a vector, A, B, C. And then you need an x naught, y naught, z naught. Okay? Doesn't matter which one you pick. It's just going to influence the point in time where you're at on the line. So let's just let x naught, y naught, z naught equal the first one. Okay, so now we have an A, a B, a C, an x naught, a y naught, and a z naught. Okay? So, x, which would equal x naught plus at, would equal 12 minus 19t. Okay? Y, which is going to equal y naught, screen, yeah, plus dt. Okay, so where's my y naught? Right there. 9 plus, oh, well, e is 0. So it's just 9. Okay? And z, which equals z naught plus ct. Okay, there's my z naught right there. That's negative 13. Okay, so these are the parametric equations that describe that line in space. Actually, let me put a note right there. So these are the parametric equations. So that's the parametric equations for those lines. All right. Now let's try to figure out what the symmetric equations are. Okay. Okay. Well, this one and this one are not too bad. You can solve for t on this one. So x minus 12 divided by negative 19 would equal z plus 13 divided by 24. Uh-oh. We don't have a t involving y. Okay, because y just equals 9. Okay, so if you end up in circumstances where you have, well, y is always 9. Y is not being influenced by t at all. So the relationship between the t's is related to x and z. Those both change with respect to time. But y is always going to remain a constant. Y is just 9. So to actually write down the symmetric equations for this guy, we put a semicolon right there and just say, well, y equals 9. Okay? So this right here is the symmetric equation of that line in space. All right. There's actually even another way that people would describe this. Instead of writing it out like this, what if we wanted to represent it in terms of I, J, and K? The x-axis, the y-axis, and the z-axis, right? So, another representation of this line. Okay, so I've got my x component right here, 12 minus 19t. So that's going to be associated with I. So I could say, well, 12 minus 19t multiplied by I, and then plus 9 times j, and then plus negative 13 plus 24t multiplied by j, k, sorry. Okay, so that's how I'm represented with i's, j's, and k's. Alright, so we'll do one more problem for this video, and then we'll start asking the question of, well, if we have lines in space, how do we determine if lines are parallel, skewed, or intersecting? That's going to be the next video. Okay. Okay, so this problem is actually pretty short. So let's say find the parametric and symmetric equations for the line that passes through say 1, 3, 2 and parallel to 4, 5. Okay, so we already have a vector that is parallel to the plane. We already have a point that exists within the plane. So basically, on a problem like this, you're just going to plug it into the formula. Okay, so this is the x naught, y naught, z naught. That's the a, b, and that's the c. So x is going to equal 1 plus 2t. Okay. Y is going to equal 3 plus 4t. And z is going to equal 2 plus 5t. All right, so this is the parametric equation that's going to be associated with this line. Let's look at the symmetric equation that is going to be associated with this line. So x minus 1 divided by 2 is going to equal y minus 3 divided by 4, and z minus 2 divided by 5. Okay, so that's the parametric and symmetric equations for this line. Not that bad to deal with, just basically plug it into the formula. Okay, what if we ask ourselves another question about this line? Okay, so like I was saying on the previous problem, depending on the way you parameterize this problem in relationship to the parametric equations up here, you can be at different points on the line, depending on how you do it. So what if we asked ourselves, at what point in time So at what point in time does this line intersect the YZ plane? I'm also going to ask at what point it actually intersects the YZ plane. But to figure out at what point it intersects that plane, I need to know that point in time. Okay. So how would I characterize this problem? I'm pausing for effect. Well, think about it. If I'm going to talk about the YZ plane, and we had a discussion about this during the last video, okay. So remember, this is X, this direction is Y, and this direction is Z. So if I am characterizing the YZ plane, what is it really? I'm just going to draw it in its first quadrant. And imagine it as being like a wall. This flat up against the YZ plane. Okay. So how would we characterize something like this? Well, X is going to equal 0. Okay, so it doesn't come out into the X dimension at all. It doesn't go backwards at all. So it's just characterized X, which equals 0. Right? So how am I going to figure out at what point in time X equals 0? And actually, this is why I actually prefer the parametric equation form, because you can plug 0 into that. Okay. So zero is going to equal 1 plus 2t. Right? Or manipulate this problem with that. We get that t is going to equal negative 1 divided by 2. Okay. So we figured out the point in time where it's actually going to intersect the YZ plane. Now let's ask the question of where does it intersect? So I know my point in time, and so I'm going to use the parametric equations, and I'm going to plug that point in time into those parametric equations. So what do we get from this? Well, I already know that X is 0, but I might as well just go ahead and plug it. We can plug the point in time. T times negative 1 divided by 2. And this is going to be 3 plus 4 times negative 1 divided by 2. Okay? And Z is going to equal 2 plus 5 times negative 1 divided by 2. Get rid of that one. Both the parentheses up. Okay, so that's going to come out to being 0. Now 3 plus 4 times negative 1 divided by 2, that's the same thing as writing this 3 plus negative divided by negative 2, 3 plus negative 2, which is 1. Okay, then the last one is 2 plus 5 times negative 1 divided by 2. You can write that as 4 divided by 2 minus 5 divided by 2, so 4 divided by 2 minus 5 divided by 2. It's going to come out to being negative 1 divided by 2. Okay, so now we know the point in time and the location of the intersection of this line with the YZ plane.